Okay, boys and girls, if you would raise your hand if you have taken geometry. Everybody raise your hand if you took geometry. Okay. How many people can tell me what it means? What does it mean?
It's the study of shapes. Earth.
What does it mean?
Earth.
Geo is earth and metry is measuring the earth. Okay, so this was the crowning glory of geometry, was that they measured the geo, right? Didn't they? Okay, so how did the geometers metry the geo? How did they measure the earth?
They used a stick and they put shadows.
Shadows and sticks.
Different places.
And places.
What was it?
Yeah.
Basically, they measured how much, they knew that the sun was at one place.
Yeah.
And they wanted to see how much the earth curved. So they would put a stick at one latitude and you would have the shadow at a certain time be so much. And you'd put a stick at another point, measure at the same time how much of a shadow was there, and you'd be able to see the curve. And if you extrapolated that all the way around to a sphere, you'd get
This is the closest anyone's ever gotten. And maybe, let me, here. Okay. Here's the Earth. Here's the North Pole. We are looking down on the Earth, yes? Okay. So there is our North Pole. Where's my planet? Got to find my... Where's the Earth? There it is. It's biting me. Okay. Here. Usually in years past, usually the kids say, well, they got a long tape measure, right? No. Here's the Earth. If you're looking at the North Pole of the Earth, it's rotating, well, it's anti-clockwise, yes? Okay? Because the east coast of the United States sees the sun before the west coast, yes? So it's rotating like this, okay? Now, here's the deal, is that if you're between the two tropics, there is a time of the year when the sun is directly overhead, correct? Yeah. Yes, so the most precise way to do this, and this was the most precise measurement, was that they took a well, and there was a well here, and wells, a well, if it's well dug, okay, goes straight down. Why are all wells, they might be quite deep, 100 feet deep, right? But they always go straight down. Why do they go straight down? Why doesn't anybody dig one at a slant?
It's the fastest way to get down.
Fastest way to get down.
And there would be a landslide.
There would be a landslide if you dug it to the side. These are all valid.
Water goes up faster.
How do you get the dirt out of a well?
Oh yeah, you need a bucket.
You lower it down. The bucket has got to go up the well without, or maybe more importantly, you've got to be able to get water out of the well with a bucket, don't you? So it's got to go straight down. All wells are dug exactly plumb, which means, barring any like anomalies in the density of the Earth's crust, that they are pointed directly toward the center of the Earth, correct? So when the sun is overhead, say the sun is like here, right? This thing is spinning anti-clockwise, right? When the sun is directly overhead, you know that it's directly overhead, and it's probably only overhead for maybe a day, a year, or something like that, right? But if you pick that particular day, the sun actually shines all the way to the bottom of the well, yes? Yes, you know it's overhead. You can look down there, oh, I see water, boom, right? I don't know how long that lasts because the wells, are very, very small angles, right? So you have one person stand here, right? One person stand here, and I suppose you could do with sticks and shadows and stuff like that, but they'd have to be plumb sticks, right? And then you go, okay, the sun's overhead now, and then you wait a little later, and actually it's going to be overhead here first, right, because the thing's rotating like this. Then you wait a little bit later, and it's overhead here, and you stop the clock, don't you? And now you know the time it took to go from this well to this well, yes? And don't you know this distance? Yeah, so the Greeks took a Jones wheel. They had Jones wheels because they had, in Greece, they had cross-country events, right? Okay, so they take a Jones wheel and measure that distance, yes? Are you picturing this? So now they know that distance, and this is all they need to know because this angle here can be calculated two ways, right? That angle is both the time it took for the sun from when it got to here over 24, right, times 2 pi, right? Isn't that right? That time is to 24, right? You can set up a proportion, right? That time is to 24 hours as that angle is to 2 pi, correct? Assuming the Earth rotates at a constant rate, which is a pretty good assumption, yeah? Okay? So we can figure out the angle that way. The angle is also equal to this distance divided by the radius of the Earth, right? Okay. So we know, don't we know S? Don't we know T? We can calculate R. And they got it, I believe, to 2 sig figs. They got it correct, right? When they measured the size of the Earth, they knew it was round. They knew that it rotated, right? Okay. And when they measured it, they actually had togas printed. They didn't print T-shirts back then. So they printed togas that showed, it said geometry on there, right? And they split it up, right? Geometry. And then it was pictures of these big hands with a tape measure, sort of measuring the Earth like that. Only the Earth was kind of a squishy Earth, and right. And they actually found one of these togas at a site. They were digging it up, and they carbon dated it, and it actually dates to the correct time in the timeline of when Euclid actually measured the Earth. So big kudo there, right? Okay. I know, isn't that amazing? So that's one baseline, right? We now know the distance from here to here, and that's a long way. That's a long way, right? So now the question is, how far away is Mars, the closest planet? Yeah? There we go. Well, in 1672, they knew, this is all they knew, right? Was they knew that Mars was, they knew the proportions, right? Because Kepler had figured out that Earth Mars is farther from the sun and Venus is closer to the sun. They didn't know what that distance was, but they knew that like Venus was 0.72 times the Earth's distance, and Mars was somewhat more, like 1 point something times the Earth's distance, right? Okay. How did they know this? From Kepler's laws, right? Kepler related the period of orbit to the radius of orbit. Yeah. Okay. But what we didn't know was we just didn't know what this distance was really. What it was in cubits and meters and stuff like that, right? Okay, so how do we figure that out? Well, to figure it out in actual meters, okay, what they had to do is they had to triangulate, right? And this is something they teach you in Boy Scouts, right? You draw a line there and you draw a line there. If you know this distance and you know this angle, can't you figure out this distance here, side to side? Can't you? Yes, you can. Okay. So how do you figure out these angles, by the way? How do you figure out that angle?
With a really big protractor.
A great big protractor. Or, let me suggest another alternative. When you look at Mars, don't you see Mars in a field of stars?
Sure.
Yes, you do. You see them in a background field of stars. Those stars are so far away that when you walk from here to here, you don't see any shift in those stars, but you see a shift because Mars is so much closer in the position of Mars, right? Let's do a little experiment here, okay? Let's cover our left eye with our left hand, hold our right finger out there, block some object. Now, the distant wall, block some object on the distant wall, that's like the distant stars. Now cover the other eye. Now look at it from the other side of the Earth. There we go. This is called a parallax shift. This is how they measure the angle, is that they see Mars against, from here they see it against different stars than these guys do. The difference in those star positions, right, is the angle that they measure. Okay, now here's the problem. The problem with this method, and this is a devilishly tricky method, okay, is that if you go out and you look at where Mars is tonight, it's in a different place tomorrow night. The word planet means wanderer, right? Yeah? Yeah, they move around in the sky a lot. In fact, Mars is crazy. Sometimes it's going forward in its orbit, then sometimes it appears to go backwards because we, of course, are an inner planet. And please be quiet. Hello? It's going we're going faster than it, so we'll pass it sometimes and see it actually go backwards. This is called retrograde motion, which doesn't make much sense unless you are thinking that they're all orbiting the sun, right? Okay. So anyway, what you have to do, and here's the problem, you can even go out tonight at 9 o'clock and measure its position exactly enough and then go out at 10 o'clock and see it in a different position. So if you were going to measure this angle and this angle, right, what do you have to do? Exactly the same time. Okay, so on this date, we're going to measure in 1672. On this date, at this time, we're going to measure it. So what they did was they got in a ship, they went all the way over to French Guinea, right, and then they called each other on their cell phones. They said, hey, are you about ready to know? I'm not set up yet. Okay, well, okay, tell me when you're going to measure, right? No, they actually chatted on Google because they didn't have cell phones, right? Yeah, they had to agree on a date. They had to be there, getting from one side